member AB. Okay. So if you look at this structure like that, we need to know what is going on at point A. Okay, we need to know what is going on at point A. Okay, so let's see what or wait. Okay, rather than knowing what is going on, okay, let's look at what is going on point A. Okay, so we are going to apply method of join. Analysis at point A now. Okay, is it point A? Yeah, at point A. We're going to do method of join analysis at point A. Okay, so we draw our point A. Right. So point A has a load coming down vertically. So point A, let me draw the gradient, the lines first. So this is for the load, and then you have a 60 degrees. Okay, so this is about my 60 degrees, and then we have a 45 degrees. Okay, so this is my about 45 degrees. Okay, so these are the lines. So this is for my AC. Okay, so this is AC line. This is my AB line, and this is my AD line. Okay, so we know that the load at AB has to be at, or AB has to carry out the compressive. Okay. So this is under what? Compression. Okay. So this over here will be your FAB. Okay, that's your FAB. Oh, let me draw better. Okay, this is not very good. Okay, so over here, okay, this is your FAB, right? So no doubt this is under compression. FAB is going that way because of Newton's third law. Action equal to action equal to reaction, same magnitude and different in direction. Okay, so action equal to reaction, same magnitude, different in direction. Okay, so now we know that over here, right? Over here, this is your ABX, and this direction will be your ABY. Let me, yeah, this over here will be your ABY. Yeah, sorry about that. So I will just put this arrow over here. This will be your ABY. So now we know that another thing that we know is that there's a load coming down here. Okay. And this is your FAC. Okay, we know that FAC is coming down. Okay. Now the confusing part, now you know all this now. Now you also have to determine what is going on AD. Okay. So if you look at point A, if you have to focus at point A, right? The thing that's disturbing us now is this ABX, right? ABX is pushing towards the right. And for point A to be stationary, ADX has to go towards the left. Okay, I repeat again, ADX has to go towards the left. Right? So this is our, I'll use a different color. We know that ADX has to go this direction. Right? To counter what? ABX, because there is no more horizontal component or X direction component. Before you do anything like this, you have to call this your X, and this is your Y, and this is the rotation about Z. Okay, so I repeat again, because of ABX is going towards the left, right? ADX has to go towards the right. So in this case, you can already design, right? You can already design the vector. Okay, so this is your what? This is your ADY, and over here, this is your FAD. And then if we were to look at the member AD, which is also the rope, right? Which is also the rope. Action is equal to reaction, same in magnitude, different induction. So this will be under what? Tensile. Okay, this will be under what? Compression. Okay, so does that make sense? Yes or no? Right? The thing is, a lot of times students get confused is what is happening in AD. So if you go back to the diagram over here, right? So we know that when you have a load coming down, right, and this AD and AC are connected by a single rope, right? So this will be, as a member, it wants to be in what? In tension. Yes or no? Right? That's what we have come up with method of joint analysis already. Okay, so now all this said and done, now we can start finding what is going on FAB. Okay, so coming back to the information that we are given, right? That we are given. So we know that P critical is equal to pi squared L squared EI. Right? Once we find out this, so we know that this P over here is in fact your F what? FAB. Okay, for buckling analysis, right? So remember, AB is under centric buckling, okay? And we realize that the load down here is compression. Only in compressive, you can induce what? Buckling. If the structure is under tension, it will not fail by buckling, okay? It will fail by yield strength, right? So coming back to over here, again, load has to induce compressive stress for buckling failure. And then we what did I mention? Well, I mentioned that intention or in tensile structure will fail by exceeding the yield strength. Okay. So this is how you write yourself. You can see we are populating what? We are populating our what? Summary sheet by just doing what? One problem. Okay. So from here we can start analyzing the problem. So from here we can identify what is FAB. Okay, first. Then when we can identify what is FAB, then we can also identify what is going on to our ABX. Okay, so we're going to start there. Okay, so we are going to find our L. So to find our L, we have to know the L or L is dependent on the on how the ends are fixed or are held. Don't say fixed where you get confused. Okay, so you look at you look over here. Okay, so if we remove support at B, what will happen to A? A will start to what? Move up and down and rotate. So at point A, right? At point A, we know that it's pin. More important thing is moment is equal to what? 0. Okay. So if you look at point B is like on a slider. So y or x is equal to 0. Y is not equal to 0. It can move up and down, but at point B, moment is equal to what? 0. Right? So over here, like at point A, x is also not equal to 0. Y is also not equal to 0. Okay, can move up and down. Okay, wait. Yeah, because what's holding here is at point D. Okay, so you look over here. So this is also pin. Okay, so when both ends are pinned, okay, pin at both ends. Pin at both ends, LE is equal to L. Right, you can see that LE is equal to L. So down here, to write that LE is equal to L. L for this case is equal to 4 meters. Yeah, we know L is equal to 4 meters. So from here, let me give more information. So also actually this question, okay, information from L2 or from material database, right? L2 steel, right? Young's modulus E is equal to 200 times 10 to the power 9 Pascal. And then we are given that stress U is equal to 703 times 10 to the power 6 Pascal. Okay. So when we come to here, you have those information. So now we are going to find our P critical. Here we're going to find out P critical. So P critical is equal to pi squared E I over L squared. Okay. So my advice is during your term test, you don't lump everything in. Okay. So you find your I first. So I on its own, the second moment of area is equal to pi over 4 multiplied by, so this is radius to power 4. Okay, so pi over 4. So the radius is equal to what? So this is 0.05 is 0.025 to power 4. Okay, so this will be equal to shift pi divided by 4 times by 0.025 power 4 is equal to 306.796 times 10 to the power minus 9 meter 4. Okay, let me do it. 306.796. Oh no, shift pi divided by 4 times by 0.025 power 4. 306 times 10 90 306 times 10 to, how come it's wait 0.025 power 4 times by shift pi divided by 4. I get 306. Hold on. 0.025 power 4 times by shift pi divided by 4. Yeah, it's 306. I'm cross-checking my answer with the textbook. Somehow it's different. Let me find out the second. I'm pretty sure the second moment of area is correct. Let me check.
I'm getting to the power of -7, then to the power of -7.
No, you don't do things like to the power 7. You have to do things like
Oh,
engine
okay.
units,
Yeah.
like to the power 9. Okay, let me find out the let me look at second moment over here. Hold on. Yeah, pi over 4 4. So radius. So I think the book is wrong. Power 4 times by shift pi power 4. So it's 306.796. This is correct. Okay. So from here, we are going to find our PCR. Okay. So PCR is equal to pi squared multiplied by 200 times 10 to the power 9. Our second moment of area is 306.796 times 10 to the power -9 divided